Fatigue assessment in Sine-on-Random environments is a major challenge for engineers. Mixed test profiles are outlined in various international standards, such as the Military Standard 810.
The time-domain rainflow approach is extremely accurate but computationally expensive, while standard frequency domain methods fail due to the non-Gaussian nature of such signals. To bridge this gap, this work examines and numerically compares innovative spectral approaches offering practical guidelines.
The identified approaches involve two main categories: a stress distribution-based approach derived from Rice's work, and power spectral density equivalence approaches, damage-based like Lalanne, Irvine, and white noise approximation methods, or energy-based like the root mean square method. Using the rainflow algorithm as baseline, performances were evaluated via damage estimates and signal representativeness. Different load cases were tested, from simple scenarios to a realistic military standard scenario. Assumptions on the fatigue life curve and other aspects were made.
The results lead to the following conclusions. Rice's method is found to be the most accurate, although only for in-band resonance conditions. Moreover, whenever multiple harmonics are involved, its computational times tend to rise. The Irvine and RMS methods yield the most correct estimates, regardless of the bandwidth and the number of sinusoids. The apparent accuracy exists despite the imperfect representation of the signal's spectrum. These methods are recommended in design and optimization phases. Lalanne's method seems to better behave in realistic multi-sign scenarios, such as military standard profiles. Since it's always conservative, it may be useful in safety-oriented design phases. The white noise method appears to lead to the least correct estimates, becoming the least preferred method in Sine-on-Random fatigue. Finally, the time domain approach is still essential. However, its application can be restricted to the critical elements identified through spectral methods, optimizing computational resources.